Okay, crew, here's a very quick screencast. I'm doing this in the common room during conference block, so it might be a little noisy. Don't forget, this is all about the mystery acid lab that you folks are working on, and we are going to have school tomorrow, so you better get it done, punks. This is how I want you to think about this. Imagine that you have two beakers, and you guys used those well plates, but essentially they hold a volume. But we're going to pretend that we have two beakers here just to make it a little easier. And we have two situations. We'll call one A and one B. And in the first beaker A, you have a 3-to-1 mix of acid to base. Now, of course, they'd be completely miscible, and they'd combine with each other. But for making this just easier for you to understand, I made it seem like they're in layers there. So in this case here, I have 2 parts base to 1 part acid. In my second scenario, I'm going to have a 1-to-1 ratio. Now, one thing I want you to pick up on here, which is important, and that is that we have the same amount of overall volume in both of these cases. So it's just been divided differently. Okay, so the same overall amount. And if you take a look at your lab handout, you'll see that the number of drops that you used in each one of the samples that you guys ran, I think had 48 drops altogether. But those 48 drops were divvied up. It might have been, I don't actually remember the numbers, but understand that they were divided up in a 2-to-1 ratio, 3-to-1 ratio, 1-to-1 ratio, 1-to-2 ratio, 1-to-3 ratio. But overall, you have the same amount of volume in any one of your samples, in any one of your tests. Similar to what we have going on here, where A and B have the same overall volume, but they've been divided up in terms of acid to base in a different ratio. Now, imagine you have a chemical equation where we have 3 parts of Q plus 1 part R leads to 1X plus a little bit of heat. Okay? Now, if that were the case, actually, I made a mistake here. Let's not make it 3 parts. Let's make it 2 parts. Okay? If this were the case, and let's say, for argument's sake, I decided to make this Q and this R. All right? So Q and R is what made this up. Now, if we had that combination, you would understand that if I combined 2 moles of A and 2 moles of Q, I'd have nothing left over. Q and R would be completely consumed, which would mean that we'd maximize the amount of X and heat that was produced. In the second scenario, though, in B, let's imagine that we had the same exact ingredients going on, still combining in a 2-to-1 ratio. But of course, in B, I don't have the 2-to-1 ratio of volumes of the liquids that we're working with. Here, it's in a 1-to-1. And of course, we still have to understand that Q needs 2 parts for every 1 part of the R. So in this case, in B, you're actually going to have some R left over. In fact, I'll draw a line here to indicate that half of your R is still going to be left over when you're done with this reaction, because if Q has to have a 2-to-1 ratio, it always is going to be in a 2-to-1 ratio to its R, and I only have 1 part Q, I'm going to have half a part of R that I'm going to use up there. So that means, in the end, which one is going to produce the most of the products here, A or B? And I think you can see pretty obviously that the A scenario is going to produce more heat than the B scenario, because the B scenario has overall fewer of those reactants to be able to combine to make the products. All right, I hope that helps you. The only other thing I want to make sure I impress upon you is that we used phenolphthalein And phenolphthalein is an indicator for base. So if there's any excess base hanging out, then the solution is going to be magenta. If all the base has been used up, however, then it's going to go to the colorless clear solution that you had initially. Okay, bye.